I'm so glad you found your way here. Right now, light from distant stars is traveling through space at 186,000 miles per second. Yet some light will never reach us, trapped forever by invisible boundaries in the cosmos. Tonight, you'll discover why gravity's grip can be absolute, and by the end, you'll understand why even light itself cannot always escape. Welcome to Sleepless Science Night. Wherever you are right now, perhaps gazing up at the darkness between stars, or simply feeling the gentle weight of gravity holding you safely to Earth, allow yourself to rest in this cosmic stillness. We'll drift through 100 space facts about black holes and their inescapable pull. From invisible boundaries where time itself stops flowing, to horizons where even light surrenders, to the moment when gravity becomes absolute. These quiet journeys through space create a cosmic community of peaceful minds. Feel free to like and subscribe or share a thought down in the comments. It helps others find their way here too, one sleepy soul at a time. It means the universe to us. Settle deeper into your pillows now. Let your shoulders drop, your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently towards sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now we begin. Black holes are regions in space where gravity becomes so powerful that nothing can escape, not even light itself. The concept emerged from Einstein's general theory of relativity in 1915, though Einstein himself doubted they could actually exist in nature. In 1916, physicist Carl Schwarzschild found the first mathematical solution describing these strange objects while serving in World War I. He calculated that if you could compress enough mass into a small enough space, gravity would become so intense that it would create a boundary from which nothing could return. The term black hole wasn't coined until 1967 by physicist John Wheeler, who needed a catchy name for these invisible objects. Before that, they were called frozen stars or collapsed stars. Today, we know they're real, scattered throughout the universe, ranging from a few times the mass of our sun to billions of times more massive. They're invisible, not because they absorb light like a sponge, but because gravity bends the fabric of space itself so severely that light cannot climb back out once it crosses a certain boundary. Every black hole has an event horizon, an invisible spherical boundary that marks the point of no return. Once anything crosses this boundary, it cannot come back, no matter how fast it tries to move. The event horizon isn't a physical surface you could touch, but rather a mathematical boundary in space, where the escape velocity equals the speed of light. Think of it like a waterfall's edge. Above the edge, you can still paddle upstream to safety, but once you go over, the current is too strong to fight. For black holes, that current is the flow of space-time itself, pulled inward by gravity. The size of the event horizon depends on the black hole's mass. The more massive the black hole, the larger its event horizon. A black hole with the mass of our sun would have an event horizon radius of about 1.9 miles, creating a sphere about 3.7 miles across. While the supermassive black hole at the center of our Milky Way galaxy, called Sagittarius A star, has an event horizon about 15 million miles in diameter. Outside the event horizon, you could theoretically escape if you had enough thrust. Inside it, all paths lead inward, no matter which direction you try to go. Space itself is flowing faster than light toward the center. Light travels at 186,282 miles per second through empty space, the fastest speed possible in our universe. Nothing can move faster than light, According to Einstein's special relativity, this cosmic speed limit is what makes black holes so absolute in their grip. Near a black hole's event horizon, you would need to travel faster than light to escape, which is physically impossible. It's not that black holes have some special force that pulls on light differently than on other things. Instead, they warp space-time so severely that all paths curve inward. Imagine trying to walk in a straight line on a surface that's tilting more and more steeply beneath your feet. Eventually, the tilt becomes so extreme that no matter which direction you face, you're always walking downhill. For light near a black hole, space-time is tilted so steeply that even traveling at the universe's maximum speed isn't enough to climb back out. The light isn't slowing down, it's still moving at its constant speed. But space itself is falling inward faster than light can cross it. This creates a region where escape becomes geometrically impossible, like trying to reach the horizon by walking on a treadmill that's moving backward faster than you can walk forward. In April 2019, astronomers quietly shared an image of a black hole's shadow, captured by the Event Horizon Telescope working patiently across Earth. This wasn't a single telescope, but a network of radio telescopes spread across Earth, working together to create an Earth-sized virtual telescope. The black hole they photographed, named M87 star, sits at the center of the Messier 87 galaxy, about 55 million light-years from Earth. It contains 6.5 billion times the mass of our Sun. In 2024, new observations revealed organized magnetic fields around M87 star, similar to those found near our galaxy's own black hole. The image shows a bright ring of glowing gas orbiting the black hole, with a dark shadow in the center where the event horizon lies. That shadow is about the size of our entire solar system. The glowing ring is material spiraling into the black hole, heated to billions of degrees by friction and gravity, shining brightly just before it crosses the point of no return. The photograph confirmed decades of theoretical predictions and proved that black holes aren't just mathematical curiosities, but real objects we can observe and study. In 2022, the same team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, confirming that the same physics applies closer to home. Black holes form when massive stars die in spectacular supernova explosions. When a star at least 20 to 25 times more massive than our Sun runs out of fuel, it can no longer support itself against its own gravity. The core collapses in less than a second, compressing matter to incredible densities. If the core's mass exceeds about 3 times the mass of the Sun, nothing can stop the collapse, not even the quantum pressure that holds atoms apart. The core continues collapsing past the point where atoms break apart, past where atomic nuclei merge, until it becomes a point of infinite density called a singularity, surrounded by an event horizon. The star's outer layers explode outward in a supernova, one of the brightest events in the universe, while the core collapses inward to become a black hole. This process happens relatively quickly. The collapse takes milliseconds, though the star's death throes may last weeks. Not all stars can become black holes, only the most massive ones. Our Sun, for instance, isn't heavy enough. When it dies in about 5 billion years, it will become a white dwarf, not a black hole. The universe has been creating black holes since the first massive stars formed, more than 13 billion years ago. Black holes come in 3 main categories, based on how they form and how massive they are. Stellar black holes form from collapsing stars and range from about 3 to 100 times the mass of our Sun. These are scattered throughout galaxies, the endpoints of massive stars' lives. Intermediate mass black holes are more mysterious, ranging from 100 to 100,000 solar masses, possibly forming when stellar black holes merge together or when dense star clusters collapse. Scientists are still studying whether these truly exist as a distinct category. Supermassive black holes lurk at the centers of most large galaxies and contain millions to billions of times the Sun's mass. Our Milky Way's central black hole, Sagittarius, a star, weighs about 4 million solar masses. The largest known supermassive black holes exceed 40 billion solar masses. How these giants formed is still debated. They may have grown by consuming gas and merging with other black holes over billions of years, or some may have formed directly from collapsing gas clouds in the early universe. In November 2024, astronomers discovered a black hole called LID 568 consuming matter at 40 times the theoretical limit, helping explain how some supermassive black holes grew so large so quickly after the Big Bang. Each type follows the same fundamental physics. Once you cross the event horizon, escape becomes impossible, but their different sizes create different environments around them. To understand why nothing can escape a black hole, we need to understand space-time itself. Einstein showed that space and time aren't separate things, but are woven together into a four-dimensional fabric. Massive objects like stars and planets create curves or dents in this fabric, similar to how a bowling ball creates a depression when placed on a stretched rubber sheet. These curves in space-time are what we experience as gravity. Smaller objects, like planets orbiting a star, follow the natural curves through space-time created by the star's mass. They're not being pulled by a force in the traditional sense, but rather following the natural paths through curved space. Black holes take this curving to an extreme, creating a steep funnel where the geometry itself becomes inescapable. Near the event horizon, space-time is curved so steeply that all paths lead inward. Even light, which always travels in straight lines through space-time, cannot escape because those straight lines all curve inward toward the black hole's center. This isn't science fiction, but confirmed physics, tested countless times through observations of planetary orbits, gravitational lensing, and now direct observations of black holes themselves. At the very center of a black hole lies the singularity, a point where all the black hole's mass is compressed into infinite density. Our current physics cannot fully describe what happens at a singularity because general relativity predicts infinite curvature, and our equations break down. Quantum mechanics, which governs the behavior of tiny particles, should become important at such small scales. But we don't yet have a complete theory that unites quantum mechanics with gravity. Some physicists think singularities might not actually exist in nature, and that a quantum theory of gravity would show something else happening instead. Perhaps a tiny region of extreme but finite density, or a connection to another region of space-time. But based on general relativity alone, once matter crosses the event horizon and continues falling inward, nothing can prevent it from reaching the singularity. The journey from event horizon to singularity can be very quick. For a stellar mass black hole, it might take only microseconds, while for a supermassive black hole, it could take hours. During this fall, tidal forces, differences in gravitational pull between your head and feet, would stretch you into a long, thin strand in a process scientists call spaghettification. But all of this would happen after crossing the event horizon, forever hidden from outside observers, who would never see you reach the singularity. One of the strangest consequences of a black hole's gravity is how it affects time itself. According to Einstein's general relativity, time moves more slowly in stronger gravitational fields. Near a black hole's event horizon, this effect becomes extreme. If you could watch someone fall toward a black hole from a safe distance, you would see them moving slower and slower as they approach the event horizon. their movements becoming sluggish like a video in slow motion. Light from them would become increasingly redshifted, meaning the wavelengths would stretch out, making them appear redder and dimmer. Eventually, they would seem to freeze just at the edge of the event horizon, forever suspended there, growing dimmer and redder until they faded from view. This isn't an optical illusion. Time really is passing more slowly for them relative to you. However, from the falling person's perspective, nothing unusual happens to their own sense of time. Their watch would tick normally, and they would cross the event horizon in a finite amount of time. They wouldn't notice anything special about the moment of crossing. This difference between perspectives is fundamental to understanding black holes. Outside observers never actually see anything cross the horizon, but from the perspective of the falling object, the crossing happens quickly and inevitably. So, yes, we're beginning to see why nothing can escape a black hole. The combination of space-time curvature and the cosmic speed limit makes escape geometrically impossible once you cross the event horizon. This isn't about needing a more powerful rocket or finding a clever trick. The very structure of space and time prevents escape. Inside the horizon, the direction outward no longer exists in any meaningful sense. All directions point inward, toward the singularity. It's as if the event horizon is a one-way membrane in space-time itself. Things can fall in, but nothing can come back out. This absolute nature of the event horizon makes black holes unique among all objects in the universe. Every other gravitational field, no matter how strong, allows escape if you have enough speed. But black holes create a boundary in space-time itself, beyond which the concept of escape becomes meaningless. And yet, as we'll discover, the story isn't quite finished. Stephen Hawking showed that black holes aren't entirely black after all, and quantum effects near the horizon might allow something to escape in an unexpected way. We're just beginning to understand how gravity becomes absolute. Near a black hole, it's helpful to think of space-time not just as curved, but as flowing, like a river flowing toward a waterfall. Far from the black hole, this flow is gentle, barely noticeable. As you get closer, the flow becomes stronger. At the event horizon, space-time flows inward at exactly the speed of light. Inside the event horizon, it flows faster than light. This means that even light itself, traveling at the universe's speed limit, cannot swim upstream against this flow. Imagine standing in a river, far from a waterfall. You can easily swim to shore. Closer to the falls, you need to swim harder. At some point, the current becomes faster than you can swim, and you're swept over. That's like the event horizon. Once you've gone over the falls, swimming harder doesn't help because the water is rushing downward faster than you can move. For black holes, that water is space-time itself, and the swimming speed limit is the speed of light. No matter how powerful your rocket engines, no matter what tricks you use, you cannot move through space faster than light, and therefore you cannot escape if space-time itself is flowing inward faster than light. Understanding escape velocity helps explain why black holes are so absolute. Escape velocity is the speed you need to completely escape an object's gravitational pull. For Earth, escape velocity is about 25,000 miles per hour. Launch something at this speed straight up, and it will leave Earth forever without needing additional thrust. For the Moon, escape velocity is much lower, only about 5,300 miles per hour, because the Moon has less mass and weaker gravity. For the Sun, it's much higher, about 1.4 million miles per hour. Now, imagine an object so massive and compact that its escape velocity exceeds the speed of light. That's a black hole. The event horizon is precisely the surface where escape velocity equals light speed. Outside this boundary, even though escape requires tremendous speed, it's still theoretically possible. Inside this boundary, you would need to move faster than light to escape, which is impossible. The more massive and compact an object, the higher its escape velocity. A black hole's mass is so concentrated that it creates an escape velocity greater than the fastest possible speed in the universe. This is why nothing can escape, not because black holes have a special gripping force, but because they compress mass so efficiently that they push escape velocity past the cosmic speed limit. In 2015, LIGO's instruments registered gravitational waves, gentle distortions in spacetime itself, created by two black holes merging far across the universe, their union sending quiet tremors through the cosmic fabric. Einstein predicted gravitational waves in 1916, but they're so faint that detecting them required incredibly sensitive instruments. When two black holes orbit each other, they gradually move closer, releasing energy in the form of gravitational waves. As they spiral inward faster and faster, the waves become stronger, reaching a crescendo at the moment of merger when the two black holes combine into one larger black hole. LIGO detected this merger as a characteristic chirp in the detector data, a signal lasting just a fraction of a second. This detection confirmed not only that gravitational waves exist, but also that black hole mergers are real events happening throughout the universe. Since 2015, LIGO and other detectors have observed dozens of black hole mergers. In October and November 2024, LIGO detected two remarkable mergers, one involving the fastest rotating black hole ever found, and another where a black hole was spinning opposite to its orbit, something never seen before. These observations continue to reveal how black holes behave when they merge and provide evidence for second-generation black holes formed from previous mergers. Black holes can spin, and some spin incredibly fast. When a massive star collapses to form a black hole, it often retains some of the star's original rotation, compressed into a much smaller space, which dramatically increases the spin rate. In October 2024, scientists detected a merger event called GW241011 involving two black holes, one with 6 times the Sun's mass and another with 20 times the Sun's mass. The larger black hole was spinning so rapidly that it's now one of the fastest rotating black holes ever discovered. Rotation affects the space around a black hole in interesting ways. A spinning black hole drags space-time around with it, creating what's called the ergosphere, a region outside the event horizon, where space-time itself is forced to rotate with the black hole. Inside the ergosphere, standing still becomes impossible. You're forced to move in the direction of the spin. But even this rotating space-time cannot help you escape if you cross the event horizon. The event horizon of a spinning black hole is slightly smaller than that of a non-spinning one with the same mass, and it's oblate rather than perfectly spherical, squashed slightly at the poles. But the fundamental property remains. Once you cross it, no amount of rotation helps you escape. The inward flow of space-time overwhelms everything. In November 2024, astronomers detected something unprecedented, a black hole merger where the larger black hole was spinning in the opposite direction from its orbit. In the merger event, GW241110, two black holes with masses of 17 and 8 times the Sun spiraled together about 2.4 billion light-years away. The larger black hole's spin axis pointed opposite to the orbital angular momentum, meaning it was spinning backward relative to the orbit, like a planet spinning clockwise while orbiting counterclockwise. This had never been observed before and suggests these black holes likely formed from previous mergers rather than directly from collapsing stars. When black holes form from stars, they typically spin in the same direction as their orbit because they inherit the rotation from the collapsing star. But when two black holes merge, the resulting black hole can end up with complex spin properties depending on the original black hole's masses and spins. This discovery provides evidence for hierarchical mergers, black holes that formed from the collision of other black holes. Even with this unusual backward spin, the fundamental physics remains unchanged. The event horizon still represents an absolute boundary, whether a black hole spins forward, backward, or not at all. Once you cross the event horizon, return becomes impossible. The spinning only affects the exact size and shape of the event horizon, not its fundamental property of being a one-way boundary in spacetime. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole containing millions or billions of times the Sun's mass. How these giants formed is one of astronomy's great mysteries. Our galaxy's central black hole, Sagittarius. A star contains about 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun. Despite its enormous mass, Sagittarius, A star, is relatively quiet right now, only occasionally consuming nearby gas or stars. Other galactic centers are more active, with black holes that constantly feed on inflowing material, creating brilliant quasars visible across billions of light years. The brightest quasar discovered, observed in light from 12 billion years ago, contains a supermassive black hole consuming material equal to about one sun's mass each day, maintaining this tremendous feeding rate for millions of years. These supermassive black holes appear to have grown steadily over cosmic time, their formation processes still revealing themselves slowly through our observations of the early universe. In November 2024, researchers discovered a black hole called LID 568 consuming matter at 40 times the Eddington limit, the theoretical maximum feeding rate, which helps explain how some black holes grew so massive so quickly. Despite their incredible size, supermassive black holes follow the same physics as stellar black holes. Their event horizons are simply much larger, and crossing one would actually be gentler. The tidal forces near a supermassive black hole's horizon are much weaker than near a small black hole's horizon. For decades, scientists assumed supermassive black holes only existed at galaxy centers. But in 2024, astronomers discovered a supermassive black hole about 2,600 light-years away from its galaxy's core, a discovery that quietly changed our understanding. The event, named AT2024-TVD, was detected when the black hole tore apart a passing star in a tidal disruption event. This wandering black hole, containing millions of solar masses, displayed the fastest changing radio signals ever recorded from such an event, with bursts of energy appearing months after the initial star destruction. The black hole, far from its expected location, revealed itself through patient observation, showing us that supermassive black holes can exist in unexpected places throughout galaxies. This finding suggests supermassive black holes can exist outside galactic centers, possibly wandering through galaxies after their host galaxies merged with larger ones, or perhaps moving along elongated orbits that occasionally bring them far from the center. The discovery changes our understanding of where black holes can hide and how galaxies evolve through mergers. It also provides evidence for gravitational wave detections. When these wandering supermassive black holes eventually spiral into their galaxy's central black hole over billions of years, they'll create tremendous gravitational waves detectable by future space-based observatories like LISA. But regardless of where they're located, these black holes maintain their fundamental property. Once you cross the event horizon, whether it's at a galaxy's heart or wandering in the outskirts, escape remains impossible. Most black holes in the universe aren't completely isolated. They have companion stars or are surrounded by clouds of gas and dust. As this material falls toward the black hole, it forms a swirling disk called an accretion disk. Friction and magnetic forces in this disk heat the material to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. Radio waves, visible light, X-rays, and gamma rays. This is why we can see black holes even though they themselves emit no light. The glowing accretion disk betrays their presence. Material in the accretion disk orbits the black hole at tremendous speeds. For a stellar mass black hole, the inner edge of the disk might orbit at 30% the speed of light, completing an orbit in milliseconds. As material spirals inward through the disk, it gradually loses energy and angular momentum, allowing it to fall closer and closer to the event horizon. At the innermost stable orbit, the closest you can orbit without inevitably falling in, the material makes its final plunge toward the event horizon, disappearing from view. The accretion disk is brightest near this innermost edge, where the material is hottest and moving fastest. Some black holes have jets, powerful beams of particles and radiation shooting outward from near the poles at nearly the speed of light, powered by magnetic fields threaded through the accretion disk. But despite all this energetic activity outside the horizon, nothing can escape once it crosses that boundary. The first strong candidate for a stellar mass black hole was Cygnus X1, discovered in the 1960s as a powerful X-ray source in the constellation Cygnus, about 6,000 light-years from Earth. Astronomers observed a massive blue supergiant star orbiting an invisible companion every 5.6 days. By studying the star's motion, they calculated the invisible object had to contain at least 15 solar masses, far too massive to be a neutron star, which meant it had to be a black hole, a black. In 2021, improved measurements showed the black hole contains about 21 solar masses. Cygnus X. One shines brightly in X-rays because its companion star is losing material, which forms an accretion disk around the black hole, heating to millions of degrees before crossing the event horizon. In 2024, the XL caliber balloon-borne telescope measured the most accurate polarization of X-rays from Cygnus X1 ever obtained, revealing details about how the chaotic, superheated material swirls around the black hole just before crossing the point of no return. These observations help scientists understand the geometry of the extreme environment just outside the event horizon. Cygnus X1 has been studied for over 50 years and helped prove that stellar mass black holes really exist in nature. The system shows us what happens when a black hole actively feeds. Tremendous energy is released outside the horizon, but everything that crosses the boundary vanishes forever. In 1974, Stephen Hawking made an astonishing discovery. Black holes aren't entirely black after all. Through a quantum mechanical process, they can slowly emit radiation and lose mass over immense timescales. Near the event horizon, quantum fluctuations constantly create pairs of virtual particles, a particle and its antiparticle that normally annihilate each other almost instantly. But at the event horizon, one particle can fall into the black hole while the other escapes as real radiation. This escaping radiation is called Hawking radiation. It's incredibly faint. For a black hole the mass of the Sun, the temperature of Hawking radiation would be approximately 62 nanokelvins, far colder than the cosmic microwave background radiation filling space. This means stellar mass and supermassive black holes are actually absorbing more radiation from their surroundings than they emit. So they're growing, not shrinking. Only extremely tiny black holes would emit significant Hawking radiation. A black hole the size of a mountain would glow with the temperature of our Sun and evaporate completely in less than a second. Hawking radiation has never been directly observed from real black holes. It's too faint. But laboratory analogues of black holes created in optical systems and flowing water have shown similar effects, supporting Hawking's theory. Recent research in 2023 suggests Hawking radiation might occur even without an event horizon, and the curvature of spacetime alone could cause objects to evaporate over cosmological timescales. If Hawking radiation is real, it means black holes eventually evaporate completely, though for stellar mass black holes, this would take trillions upon trillions of years, far longer than the current age of the universe. In the 1970s, physicists discovered that black holes obey laws similar to the laws of thermodynamics, the physics of heat, energy, and entropy. Jacob Bekenstein showed that a black hole's entropy, a measure of its disorder or information content, is proportional to the surface area of its event horizon, not its volume. This was revolutionary because most objects' entropy depends on their volume. The larger the event horizon, the more entropy the black hole contains. Stephen Hawking extended this by showing that black holes have a temperature related to their mass, confirming their thermodynamic objects. The laws of black hole thermodynamics parallel the classical laws. The surface area of a black hole can never decrease, similar to how entropy never decreases. And you can't reduce a black hole's temperature to absolute zero in a finite number of steps. In September 2025, LIGO confirmed the area theorem by observing a black hole merger. The final merged black hole had a surface area at least as large as the sum of the two original black holes' areas, exactly as predicted. This thermodynamic behavior seems strange because it treats event horizons, mere boundaries in spacetime, as if they have physical properties like temperature and entropy. This deep connection between gravity, quantum mechanics, and thermodynamics suggests our universe operates on principles we're still uncovering. But from a practical standpoint, the thermodynamics don't change the fundamental fact. The event horizon remains a one-way boundary. Black holes create a profound puzzle called the information paradox. In quantum mechanics, information is never truly destroyed. If you know the exact quantum state of a system now, you can, in principle, calculate what it was in the past and what it will be in the future. But what happens to information when it falls into a black hole? If a black hole eventually evaporates completely through Hawking radiation, and that radiation appears to be completely random with no information about what fell in, then the information seems to vanish forever, violating quantum mechanics. Stephen Hawking initially argued that black holes do destroy information, which would require modifying quantum mechanics, but this created fierce debate. Some physicists proposed that information might be encoded in subtle correlations in the Hawking radiation. Others suggested a firewall at the event horizon that would destroy information carrying patterns, but would also violate other principles of physics. More recently, physicists working with string theory and quantum field theory have proposed entanglement islands, regions where information from inside the black hole becomes encoded on the event horizon surface in subtle quantum entanglements. In 2019, researchers showed these islands might extend slightly beyond the event horizon in ways that could, in principle, be detected. While the paradox isn't fully solved, most physicists now believe information is preserved somehow, perhaps encoded in ways we don't yet fully understand. The question keeps physicists awake at night. How can nothing escape? Yet information must be preserved. In July 2025, NASA's James Webb Space Telescope made an intriguing discovery: possible evidence of a direct collapse black hole forming in real time. Researchers Peter Van Dokkum and Gabriel Brammer found an unusual galaxy nicknamed the Infinity Galaxy because of its shape. Two compact red nuclei surrounded by rings, resembling an infinity symbol. This galaxy resulted from a head-on collision between two disk galaxies. What makes it extraordinary is that a supermassive black hole sits between the two nuclei, within a vast expanse of gas, rather than inside either nucleus. The team proposes this black hole formed directly from the collapsing gas cloud itself, rather than growing slowly over time. This direct collapse process might explain how some supermassive black holes in the early universe grew so massive so quickly. Instead of forming from a stellar mass black hole and gradually accreting matter over billions of years, they could form already massive from collapsing gas. The discovery provides the best evidence yet for this formation pathway. Regardless of how a black hole forms, From a collapsing star, from merging black holes, or directly from collapsing gas. Once the event horizon forms, the same rules apply. The mass and energy become trapped behind an absolute boundary from which nothing escapes. Sagittarius, a star. The supermassive black hole at the center of our Milky Way galaxy sits roughly 27,000 light-years from Earth. In 2022, the Event Horizon Telescope collaboration released the first image of this black hole, showing a glowing ring of heated material orbiting the dark shadow of the event horizon. The black hole contains about 4 million times the Sun's mass, but is relatively quiet compared to actively feeding black holes in other galaxies. Still, astronomers occasionally observe flares when clumps of gas or dust fall toward it. In 2024, new observations revealed that Sagittarius A star has well-organized magnetic fields similar to the much more massive black hole M87 star, hinting that our galaxy's central black hole might have an undiscovered jet, a beam of particles shooting outward near the speed of light. Sarah Issaoun, the research co-leader, noted that strong magnetic fields are linked to jet formation, and since Sagittarius A star has similar geometry to M87 star, there might be a jet waiting to be observed. The black hole's event horizon is about 15 million miles across, roughly the size of Mercury's orbit around the Sun. Despite being at our galaxy's heart, Sagittarius, a star represents no danger to Earth. We're far too distant to feel its gravitational influence directly, but its presence reminds us that our galaxy, like most large galaxies, contains an object at its center where gravity has become absolute and escape is impossible. Halfway through our first set of facts, the answer to why can nothing escape a black hole is becoming clear. It's not about strength of pulling or magical forces that grab and hold. Instead, it's about the fundamental structure of space and time. General relativity shows us that gravity isn't a force pulling on objects, but rather a curvature of space-time itself. Black holes compress mass so intensely that they curve space-time to its extreme limit. At the event horizon, this curvature becomes so severe that all paths through space-time, every possible direction you could move, lead inward toward the center. Light itself, always moving at the universe's maximum speed, follows the geometry of space-time. When space-time curves so steeply that even light's path bends inward, nothing can escape because nothing can travel faster than light to overcome that inward geometry. The cosmic speed limit, the speed of light, combines with the extreme warping of space-time to create an absolute boundary. Quantum mechanics adds a subtle twist through Hawking radiation, suggesting black holes aren't completely black over immense timescales. But for anything crossing the event horizon, the answer is clear and unchangeable. Escape becomes geometrically impossible. The barrier isn't made of matter or energy, but of space-time itself, folded into an inescapable geometry. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The telescopes we build, the instruments we point toward the heavens, all made from the material of the universe. Studying the universe, feel yourself carrying the trace of ancient stars. Every observation we make, we're using starlight to study the darkness between stars. We are all cosmic travelers, flying on a small planet through the galaxy. Now we continue. The speed of light, 186,282 miles per second, isn't just the speed at which light travels. It's the maximum speed at which anything in the universe can move or transmit information. Einstein's special relativity established this cosmic speed limit in 1905. Nothing with mass can reach light speed, no matter how much energy you use to accelerate it. As an object approaches light speed, its mass effectively increases, requiring ever more energy to accelerate further. Reaching light speed would require infinite energy, which is impossible. This limit applies to everything: spacecraft, particles, even information. When you push on something, the information you're being pushed can't travel through the object faster than light speed. This fundamental limit is what makes black holes so absolute. Inside the event horizon, you would need to exceed this cosmic speed limit to escape, which physics tells us is impossible. No technology, no matter how advanced, can overcome this limitation because it's built into the fabric of reality itself. Near a black hole, tidal forces become extreme. Tidal forces arise because gravity weakens with distance. The side of an object closer to a massive body experiences stronger gravity than the far side. On Earth, tidal forces from the moon create ocean tides. But the effect is gentle. Near a black hole, tidal forces are so strong they would stretch you like taffy in a process scientists call spaghettification. Imagine falling feet first toward a black hole. Your feet, being closer, would be pulled harder than your head, stretching you vertically while simultaneously compressing you horizontally, like squeezing a tube of toothpaste. For a stellar mass black hole, spaghettification would begin well before you reach the event horizon, tearing you apart, atom by atom. For a supermassive black hole, the tidal forces at the horizon are much gentler. You could actually cross the horizon intact and survive for some time before tidal forces deeper inside became lethal. Either way, once you cross the horizon, the increasing tidal forces as you approach the singularity would eventually overcome any material strength. All matter falling into a black hole ultimately faces the same fate: stretched, compressed, and finally reaching the singularity at the center. Very close to a black hole, orbits become unstable. There's a special radius called the innermost stable circular orbit, or ISCO, marking the closest distance at which matter can orbit indefinitely. Inside this radius, orbits decay rapidly. Anything there spirals inward and crosses the event horizon within a few orbits at most. For a non-spinning black hole, the ISCO is at 3 times the radius of the event horizon. For a spinning black hole, it can be closer. Material in an accretion disk orbits down to the ISCO, then plunges inward, disappearing from view as it crosses the event horizon. At the ISCO around a stellar mass black hole, material orbits at about 30% of light speed, experiencing tremendous gravitational forces and heating to millions of degrees. Even closer, within the event horizon, the concept of a stable orbit becomes meaningless. Everything moves inexorably inward, regardless of its speed or direction. Interestingly, at certain distances just outside the event horizon, light itself can orbit the black hole in what's called a photon sphere, but these orbits are unstable. The slightest disturbance sends the light either escaping to infinity or falling across the horizon. Black holes bend light passing nearby, creating a phenomenon called gravitational lensing. Light traveling from a background star or galaxy, if it passes near a black hole, follows the curved spacetime around it, bending its path like glass bends light in a lens. This can create multiple images of the same background object, or stretch the background into arcs and rings. Einstein predicted this effect in 1915, and it was first observed during a solar eclipse in 1919, when stars near the sun's edge appeared shifted from their true positions. Around black holes, lensing becomes extreme. The glowing rings seen in Event Horizon Telescope, images of M87 star and Sagittarius A star, is partially due to lensing. Light from the backside of the accretion disk is bent around the black hole, allowing us to see material behind the black hole. The dark shadow in the center is larger than the event horizon itself, because light approaching too closely gets captured. Gravitational lensing doesn't help you escape a black hole, but it does show how profoundly black holes warp space-time. In physics, black holes are described by the no-hair theorem, a somewhat playful name for a profound principle. The theorem states that black holes are completely characterized by just three properties: mass, electric charge, and angular momentum or spin. Everything else about the matter that formed the black hole, what it was made of, its shape, its history, is lost forever. This is what physicists mean when they say black holes have no hair, no distinguishing features beyond those three numbers. Whether you make a black hole from hydrogen, iron, old computers, or even light itself, if they have the same mass, charge, and spin, they're identical. All the complex information about the original matter disappears behind the event horizon. From outside, you cannot tell what fell in. This simplicity is both elegant and troubling. It makes the mathematics of black holes remarkably clean, but it raises deep questions about information and what happens to the quantum states of matter crossing the horizon. Spinning black holes drag space-time around with them as they rotate, an effect called frame dragging or the lens-thurring effect. Imagine a spinning ball in thick honey. The honey near the ball gets pulled around with it. Similarly, a spinning black hole drags space-time, forcing anything nearby to move in the direction of the spin. The region where this happens most dramatically is called the ergosphere, which lies outside the event horizon. Within the ergosphere, space-time itself rotates faster than light, and standing still becomes impossible. You're forced to rotate with the black hole whether you want to or not. However, in the ergosphere, you can still escape if you have enough energy. The event horizon lies within the ergosphere, and once you cross that boundary, frame dragging no longer matters because you cannot escape regardless. Frame dragging has been measured around Earth using satellites. Our planet's rotation drags space-time very slightly, exactly as predicted. Near black holes, the effect becomes extreme. Inside a black hole's event horizon, something strange happens to time and space. They effectively trade roles. Outside the horizon, you can move freely through space, but are forced to move forward through time. Inside the horizon, the singularity isn't just a place, it's a moment in your future timeline, approaching with the same inevitability as the next tick of a clock. In this region, the singularity becomes an event in your future, as unavoidable as tomorrow. You can no more avoid hitting the singularity than you can avoid moving into the next second of time. This role reversal helps explain why escape is impossible. Outside, inward, and outward are spatial directions you can choose between. Inside, inward becomes the future direction of time, and outward becomes the past. Just as you cannot travel backward in time to yesterday, you cannot move outward to escape. The singularity lies in your future, and all paths through time lead to it. In the 1970s, Jacob Bekenstein proposed a remarkable connection. A black hole's entropy, a measure of hidden information, is proportional to the surface area of its event horizon, not its volume. For a sphere, area equals 4 pi r squared, where r is the radius. For a black hole, area relates to entropy through Planck units, fundamental units combining quantum mechanics and gravity. This means as a black hole absorbs matter or energy, its horizon grows and its entropy increases. The connection between area and entropy suggests the event horizon isn't just a mathematical surface, but something physically meaningful. It implies that information about everything that fell into the black hole is somehow encoded on the horizon's surface, like a hologram encoding three-dimensional information on a two-dimensional surface. This led to the holographic principle, the idea that our three-dimensional universe might be described by information encoded on a two-dimensional boundary. Some supermassive black holes are incredibly active, consuming vast amounts of matter and releasing tremendous energy. These are called active galactic nuclei, and the brightest ones are quasars, objects so luminous they can outshine entire galaxies, containing hundreds of billions of stars. A quasar's brightness comes from the accretion disk around a feeding supermassive black hole. As material spirals inward at nearly light speed, friction and magnetic forces heat it to millions of degrees, creating intense radiation across the electromagnetic spectrum. The brightest quasar known, powered by a black hole 17 to 19 billion times the Sun's mass, emits so much light it took 12 billion years to reach us, meaning we see it as it was in the universe's early history. This monster consumes the equivalent of one sun's mass in gas every day. Yet despite this tremendous energy output, none of it comes from inside the event horizon. It all originates from material still outside, just before crossing the point of no return. Magnetic fields play a crucial role in the dynamics of material around black holes. In 2024, observations of Sagittarius A star revealed well-organized magnetic fields near the event horizon, similar to those around M87 star. These fields are generated by electrically charged particles in the accretion disk and can become incredibly strong, up to trillions of times stronger than Earth's magnetic field. The fields thread through the disk and help transfer energy and angular momentum, allowing material to spiral inward. They may also launch jets, narrow beams of particles shooting away from the black hole at nearly light speed, perpendicular to the accretion disk. The exact mechanism for launching these jets isn't fully understood, but it involves magnetic fields extracting rotational energy from the spinning black hole or the inner accretion disk. In October 2025, researchers showed through simulations that magnetic reconnection, when magnetic field lines break and reconnect in new configurations, powers M87 star's immense particle jet. Black holes reveal themselves through X-ray emissions from material heating up in accretion disks. X-rays are high-energy photons that require tremendous temperatures, millions of degrees, to produce. Several X-ray space telescopes, including NASA's Chandra X-ray Observatory and ESA's XMM Newton, have observed hundreds of black holes. In 2024, the XL Caliber balloon-borne telescope measured X-ray polarization from Cygnus X1 with unprecedented accuracy, revealing how light from the chaotic, superheated material near the event horizon becomes organized by extreme conditions. X-ray observations show the inner regions of accretion disks, where material makes its final plunge toward the event horizon. The X-ray spectrum, how bright the source is at different X-ray energies, tells astronomers about the temperature and motion of the material. Rapid variations in X-ray brightness, sometimes on timescales of milliseconds, reveal changes in the innermost regions. Many black holes exist in binary systems with a companion star. The black hole's gravity pulls material from the companion, forming an accretion disk. Depending on the companion's type and proximity, mass transfer can be gradual or dramatic. If the companion is a massive star, it loses mass through a stellar wind that the black hole captures. If it's a lower mass star filling its gravitational boundary called the Roche lobe, material streams directly from the star to the black hole. In some systems, astronomers observe jets and outflows, material being ejected at high speeds, even as other material falls in. These binary systems eventually evolve, and if the companion is also massive enough, it will eventually collapse to form a second black hole. The two black holes then orbit each other, slowly spiraling closer by emitting gravitational waves, eventually merging in a dramatic collision. Between stellar mass black holes and supermassive ones, there may be intermediate mass black holes containing hundreds to thousands of solar masses. Evidence for these is less certain than for the other types. They might form when dense star clusters collapse, or when stellar mass black holes merge together repeatedly. In 2020, LIGO detected a merger involving black holes of 85 and 65 solar masses, creating a final black hole of about 142 solar masses. The first clear evidence for an intermediate mass black hole. Finding more of these objects would help explain how supermassive black holes grow so large. If intermediate mass black holes exist in sufficient numbers and merge over time, they could be the seeds that grow into the supermassive monsters at galaxy centers. Some theories suggest tiny black holes might have formed in the very early universe, shortly after the Big Bang, when the universe was extremely hot and dense. These hypothetical primordial black holes wouldn't form from collapsing stars, but from density fluctuations in the primordial plasma. If the early universe had regions slightly denser than average, gravity might have compressed them into black holes before the universe expanded too much. Depending on conditions, these primordial black holes could have a wide range of masses. Some might be tiny, lighter than asteroids, while others could be planetary mass or larger. Very small primordial black holes would evaporate rapidly through Hawking radiation and would be long gone by now. Larger ones could still exist, and some physicists speculate they might constitute some or all of the dark matter we detect but cannot see. Through these varied observations, gravitational waves, X-rays, radio emissions, photographs of glowing accretion disks, our understanding of why nothing can escape a black hole has deepened. It's not one simple answer, but a combination of fundamental physics. Einstein's general relativity describes how mass curves spacetime, creating the geometry of the event horizon. Special relativity establishes the speed of light as an absolute limit, ensuring nothing can move fast enough to escape. Once spacetime flows inward faster than light. Quantum mechanics adds Hawking radiation, suggesting information isn't permanently lost even if matter cannot return. Thermodynamics shows that event horizons have entropy and temperature, behaving like physical objects even though they're just boundaries in spacetime. Observations from Earth and space confirm these theories, showing us real black holes behaving exactly as predicted. You're here with me now, perhaps awake, perhaps drifting between thoughts. Take a slow breath. Notice how your body feels a little lighter, as if gravity has softened its hold. We're wandering through the cosmos together, you and I, and anyone else listening in the darkness. Each fact like a dim star we pass slowly, without hurry. Just drifting. There's no rush, no destination. Just the gentle momentum of curiosity carrying us forward. Let's continue. From a safe distance, watching something fall toward a black hole creates a strange perspective. You would see the falling object slow down as it approaches the event horizon, its movements becoming more and more sluggish until it appears frozen just at the edge. Never quite crossing. Light from the object would become increasingly redshifted, wavelengths stretching longer, colors shifting toward red and then infrared and radio waves, growing dimmer and dimmer. Within seconds, the object would fade from visibility entirely, effectively frozen at the horizon from your perspective. This isn't an illusion. Time really does pass differently near the horizon compared to far away. The gravitational time dilation becomes so extreme that an infinite amount of time as measured by distant clocks passes, while the falling object experiences only finite time crossing the horizon. From the perspective of someone falling toward a black hole, the experience is completely different. You wouldn't notice anything special as you cross the event horizon. No wall, no barrier, no sensation marking the point of no return. Your watch would tick normally, your surroundings would look continuous, and the crossing would happen in finite time, perhaps seconds for a stellar mass black hole, or hours for a supermassive one. You might not even realize you'd crossed until you tried to turn around and found it impossible. Looking outward, you would see the universe above you appearing blue-shifted, with time seeming to pass faster for the outside world. Looking toward the singularity, space itself becomes increasingly distorted. The tidal forces would grow stronger, eventually becoming lethal. This difference in perspectives creates a fascinating paradox. From outside, you never see anything actually cross the horizon. Objects appear to freeze and fade just outside. From the falling object's perspective, it crosses smoothly in finite time. Both perspectives are equally valid. There's no absolute correct viewpoint. This isn't a contradiction, but a feature of relativity. Time and simultaneity depend on your reference frame. Events that are simultaneous in one frame aren't necessarily simultaneous in another. The external observer and the falling observer disagree about when or if the crossing happens because they're using different time coordinates. This paradox highlights something profound. The event horizon isn't a physical thing sitting in space, but rather a feature of space-time geometry that appears different from different perspectives. The mathematics of general relativity allows for an object called a white hole, essentially a black hole running backward in time. While a black hole's event horizon allows things to fall in but not come out, a white hole's horizon would allow things to come out but not fall in. White holes would be the time reverse of black holes, spewing matter and energy outward. No white holes have ever been observed, and most physicists think they don't exist in nature. The reason is related to entropy. Black holes represent maximum entropy for a given region of space, the most disordered state possible. White holes would be extremely ordered, requiring special initial conditions that seem incompatible with how our universe evolved. Still, they remain a theoretical curiosity, allowed by the equations but not by nature. Popular science fiction often features wormholes, tunnels through space-time connecting distant regions of the universe or even different universes. Einstein's equations do allow wormhole solutions, technically called Einstein-Rosen bridges. A wormhole would have two mouths, each resembling a black hole's event horizon, connected by a throat through higher dimensional space. Theoretically, you could enter one mouth and emerge from the other, bypassing the normal space between them. However, calculations show that wormholes, if they could exist, would be incredibly unstable, collapsing almost instantly unless held open by exotic matter with negative energy density, something we've never observed and that might not exist. Even if a wormhole could somehow be stabilized, it wouldn't help you escape from inside a black hole's event horizon. General relativity's equations theoretically allow for singularities without event horizons, called naked singularities. These would be regions of infinite density visible to the outside universe, not hidden behind a horizon. However, physicist Roger Penrose proposed the cosmic censorship hypothesis, suggesting nature abhors naked singularities and always hides them behind event horizons. No naked singularity has ever been observed, supporting this hypothesis. If naked singularities existed, they would be problematic because they'd allow information from regions of infinite curvature to escape, potentially making physics unpredictable. The event horizon serves as a kind of quarantine, hiding the singular region where our physics breaks down and preventing it from affecting the rest of the universe. While the simplest black holes are described by the Schwarzschild solution, non-rotating and uncharged, real black holes can spin and carry electric charge. A rotating black hole is described by the Kerr solution, which includes an ergosphere and a smaller event horizon than a non-spinning black hole of the same mass. A charged black hole follows the Reissner-Nordström solution, with event horizon properties depending on the charge. In principle, a black hole could both spin and be charged, following the Kerr-Newman solution, the most general case. However, most astrophysical black holes probably have negligible electric charge because the universe contains roughly equal amounts of positive and negative charge, and any imbalance would quickly neutralize. Astronomers can measure how fast a black hole spins by observing X-rays from the inner accretion disk. The innermost stable orbit depends on spin. For a maximally spinning black hole, it can be very close to the horizon, while for a non-spinning one, it's farther out. By measuring where the inner disk edge lies, astronomers infer the spin. X-ray reflections from the disk, iron atoms absorbing and re-emitting X-rays, show characteristic patterns that shift and distort due to the disk's motion and the black hole's gravitational lensing. By analyzing these patterns, researchers can determine both spin rate and orientation. The October 2024 detection of one of the fastest spinning black holes ever found came from gravitational wave analysis. The spin affects the gravitational wave signal's characteristics. On the largest scales, the universe expands, driven by dark energy, a mysterious component making up about 68% of the universe's total energy. Dark energy causes the expansion of space to accelerate, pushing distant galaxies away from each other faster and faster. Interestingly, dark energy doesn't significantly affect individual black holes. Their gravity is so strong locally that the expansion of space around them is negligible. They don't expand with the universe. The event horizon's size depends only on the black hole's mass, charge, and spin, not on the universe's expansion. However, dark energy does affect the fate of black holes over immense timescales. As the universe expands and matter becomes more diluted, black holes will grow by consuming nearby matter, but won't find new sources to feed on. We've reached the midpoint of our wandering through black hole physics. We've seen why escape is impossible. Space-time curves so severely at the event horizon that all paths lead inward, and the cosmic speed limit prevents anything from moving fast enough to overcome that geometry. We've learned that different observers see the horizon differently, but all agree that once crossed, return is impossible. We've explored how black holes form, how they spin, how they interact with their surroundings, and how they reveal themselves through gravitational waves and radiation from material just outside the horizon. The answer to our question is clear in its physics, but deep in its implications. Black holes represent not just extreme gravity, but boundaries in the very structure of space-time. Let each breath remind you softly. Time flows at its own pace for everyone. Your moments belong to you, happening gently, uniquely, at a rhythm that's yours alone. While the vast universe continues to spin, expand, change, this second, you're breathing, listening, is yours. Notice the present moment, knowing that right now, your time flows at its own gentle pace. Nowhere else in the universe, but here, in your awareness. And we continue drifting. Supermassive black holes at galaxy centers play an important role in galaxy evolution. When these black holes actively feed, the energy released can heat gas throughout the galaxy, regulating star formation. Too much black hole activity can blow gas out of the galaxy, temporarily stopping star formation. Too little, and gas might collapse to form stars too rapidly. Observations show a correlation between a galaxy's central black hole mass and properties of the galaxy's stellar bulge, suggesting black holes and their host galaxies co-evolve. The relationship isn't fully understood, but simulations suggest feedback from active black holes shapes galaxies over billions of years. The 2019 and 2022 Event Horizon Telescope images represent humanity's first direct observations of event horizons. These images required coordinating radio telescopes across Earth to achieve resolution equivalent to an Earth-sized telescope. The shadow visible in the images is slightly larger than the event horizon itself. It includes the photon sphere, where light orbits the black hole before either escaping or falling in. The glowing ring is synchrotron radiation from electrons spiraling in magnetic fields just outside the horizon, heated to billions of degrees. Future observations with additional telescopes, possibly including space-based dishes, will provide sharper images and movies showing how material swirls and falls. Cygnus X. One remains one of the most studied black holes, orbiting a blue supergiant star every 5.6 days. The system is close enough, about 6,000 light-years away, that we can observe it in detail. The black hole strips material from its companion star, forming an accretion disk that glows brilliantly in X-rays. The system sometimes shows jets, beams of particles shooting outward at nearly light speed. In 2024, the XL caliber telescope measured the polarization of X-rays from Cygnus X1 with record precision, revealing how magnetic fields organize the chaotic material near the event horizon. Our galaxy likely contains tens of millions to hundreds of millions of stellar mass black holes, the remnants of massive stars that died long ago. Most are invisible, drifting through space without companion stars or nearby gas to create glowing accretion disks. We've detected only a few hundred, mostly in binary systems where they reveal themselves by affecting their companions. Occasionally, a black hole might pass close to a star, stripping material and creating a temporary X-ray source before wandering away. Gravitational wave detectors have added a new way to find black holes, detecting the gravitational waves when two merge. Theoretical physicist Roger Penrose proposed a way to extract energy from a spinning black hole using the ergosphere, a region outside the event horizon where spacetime is dragged around the black hole. In the Penrose process, an object enters the ergosphere and splits into two pieces. One piece falls into the black hole with negative energy relative to infinity, while the other escapes with more energy than the original object had. This seemingly violates energy conservation, but actually extracts rotational energy from the black hole, slightly slowing its spin. A similar process involving magnetic fields, the Blandford-Znajek mechanism, might power some of the jets seen from active black holes. Some physicists have proposed that when black holes merge, there might be echoes in the gravitational wave signal, subtle reverberations caused by quantum effects near the event horizon. If quantum gravity modifies the horizon structure slightly, replacing it with something like a very stiff membrane, gravitational waves might partially reflect off it, creating echoes after the main signal. Researchers have searched for these echoes in LIGO data, with controversial results. Some claim to have found hints, while others find no convincing evidence. If echoes exist, they would reveal quantum gravity effects at work near horizons. Science fiction often features black holes as potential time machines, but the reality is more constrained. Rotating black holes have complex interiors with structures called inner horizons and regions where closed time-like curves might exist, paths through spacetime that loop back to their starting point in time. However, reaching these regions would require passing through the outer event horizon first, from which escape is impossible. Even if you reach the interior regions with their exotic properties, you couldn't return to tell anyone about it. Theoretical physicists debate whether these interior structures are physically real or artifacts of idealized mathematical solutions. LIGO detects gravitational waves by measuring incredibly tiny changes in distance, smaller than the width of a proton, caused by passing distortions in the fabric of space. Each detector consists of two 2.5-mile-long arms arranged in an L shape. A laser beam travels up and down each arm, bouncing between mirrors. When a gravitational wave passes, it stretches space in one direction, while compressing it in the perpendicular direction, changing how far the light travels. By comparing the two arms' light travel times, LIGO detects the wave. Because gravitational waves are so faint, detectors must be extraordinarily sensitive, isolating the mirrors from ground vibrations, temperature changes, and countless other disturbances. The information paradox remains one of physics' deepest puzzles. When matter falls into a black hole, quantum information about its state disappears behind the horizon. If black holes eventually evaporate through Hawking radiation that appears random, the information seems lost forever. Yet quantum mechanics says information cannot be destroyed. Recent work suggests information might be preserved in subtle quantum correlations in the Hawking radiation. But extracting that information would be impossibly complex. Other ideas propose information might be encoded on the event horizon surface in Planck scale details. The holographic principle suggests the horizon contains all information about the interior. The dark center visible in event horizon telescope images is called the black hole's shadow. It's larger than the event horizon itself because it includes light that barely missed being captured, photons that passed just close enough to be deflected away but didn't fall in, creating a dark region. The shadow's size depends on the black hole's mass and spin. For a non-spinning black hole, the shadow is exactly 2.6 times the horizon radius. Spin can shrink this slightly. The shadow's shape reveals spin orientation. A spinning black hole creates a slightly asymmetric shadow. By measuring shadows precisely, astronomers can test general relativity's predictions and rule out alternative gravity theories. Among the quiet events in deep space, gamma-ray bursts mark moments when massive stars transform into black holes, releasing brief flashes of light that travel across the cosmos, fading gently into the darkness. When a very massive star collapses, it can create a black hole surrounded by a temporary accretion disk of infalling material. Magnetic fields threading through this disk can launch two narrow jets of particles and radiation traveling at nearly light speed. If one of these jets points toward Earth, we observe a gamma-ray burst, a flash of high-energy photons, lasting seconds to minutes, detectable across vast distances. Black holes provide laboratories for testing Einstein's general relativity in its most extreme form. Near the event horizon, space-time curvature reaches its limit, and velocities approach light speed, conditions impossible to replicate anywhere else. Observations of black holes test whether relativity's predictions hold in these extreme environments. So far, every test confirms Einstein's theory. Gravitational wave signals match predicted patterns precisely. Event horizon images show shadows the predicted size and shape. The area theorem holds. Black holes' surface areas never decrease. Tests of the no-hair theorem show black holes are indeed characterized only by mass, charge, and spin. When a black hole orbits another compact object, another black hole, a neutron star, or a white dwarf, the system gradually loses energy by emitting gravitational waves, causing the orbit to shrink over millions of years. Eventually, the two objects spiral together rapidly in the final seconds, releasing tremendous gravitational wave energy before merging. For black hole pairs, the merger creates a larger black hole. For black hole-neutron star pairs, the black hole typically swallows the neutron star whole if the black hole is much larger, or might tidally disrupt it if masses are similar, briefly creating a firework of ejected neutron-rich material. At the event horizon, quantum effects should become significant at the Planck scale, distances of about 10 to the negative 35 meters, where the smooth spacetime of general relativity might give way to a grainy quantum structure we cannot yet fully describe. Hawking. Radiation arises from quantum vacuum fluctuations near the horizon. Particle-antiparticle pairs, where one falls in and one escapes. The information paradox stems from conflict between quantum mechanics. Information is preserved, and classical black holes, information lost. Proposals to resolve these conflicts often involve quantum gravity, a theory uniting quantum mechanics and general relativity, which we don't yet have. 3/4 through our journey, we can see how deeply physicists have come to understand black holes despite their mysterious nature. We know they form from collapsing stars, grow through mergers and accretion, and exist in 3 main types from stellar to supermassive. We photographed their shadows, detected their mergers, measured their spins, observed their effects on surrounding matter, and confirmed they follow relativity's predictions precisely. We understand why nothing can escape. The combination of space-time curvature and the cosmic speed limit creates an absolute boundary. We've identified mysteries remaining: the information paradox, the interior structure, quantum gravity effects, but we've mapped the territory well. Next-generation instruments will reveal black holes in unprecedented detail. The Event Horizon Telescope continues expanding, adding telescopes to improve resolution and enable movies showing material orbiting and falling in. Space-based telescopes might join the network, dramatically improving image quality. The LISA space mission, planned for the 2030s, will detect gravitational waves from supermassive black hole mergers across the universe, revealing how these giants form and grow. More sensitive ground-based detectors will find black hole mergers farther away and fainter signals. X-ray telescopes with better sensitivity will probe closer to event horizons, testing relativity more precisely. In a sense, black holes are cosmic recycling centers. Stars fuse light elements into heavier ones throughout their lives, creating the carbon, oxygen, and iron that make up planets and life. When massive stars die and form black holes, those elements get locked behind event horizons, removed from the cosmic cycle. Material that falls into supermassive black holes, gas, dust, occasional stars, also disappears from the visible universe over immense timescales. If Hawking radiation is real, black holes slowly return their mass as radiation. But this radiation is essentially thermal energy, not matter with structure. The universe's matter is gradually being locked away inside horizons. Every object has a Schwarzschild radius, the radius to which you'd need to compress it to create a black hole. For Earth, this radius is about 0.35 inches. Compress Earth's entire mass into a sphere that small, and it would become a black hole. For the Sun, the Schwarzschild radius is about 1.9 miles. A human body's Schwarzschild radius is about 10 to the negative 25 meters, far smaller than an atom. The equation is simple. R equals 2gm divided by c squared, where g is the gravitational constant, m is mass, and c is light speed. This radius defines where the escape velocity equals light speed. When a star passes too close to a supermassive black hole, tidal forces can tear it apart in a tidal disruption event. Half the star's material falls into the black hole, creating a bright flare lasting months as the material heats in a temporary accretion disk. The other half is ejected into space. These events are rare in any given galaxy, perhaps once every 10,000 years, but telescopes now monitor millions of galaxies, catching several tidal disruptions annually. In October 2024, astronomers observed AT 2024 TVD, a tidal disruption event by a black hole 2,600 light-years from its galaxy center. The first such event observed outside a galactic nucleus. Active supermassive black holes create powerful winds, outflows of gas driven by radiation pressure from the bright accretion disk or by magnetic forces in jets. These winds can blow at thousands of miles per second, carrying mass equivalent to hundreds of suns per year outward from the galactic center. The winds collide with gas in the galaxy, heating it and sometimes driving it out of the galaxy entirely. This feedback regulates star formation. Less gas means fewer new stars. Some galaxies show evidence of past powerful quasar phases that cleared out most of their gas, essentially shutting down star formation. Black holes can spin rapidly, but there's a maximum spin rate. If a black hole spun faster, the event horizon would disappear, leaving a naked singularity, which cosmic censorship suggests doesn't happen in nature. The spin limit is characterized by a dimensionless spin parameter that ranges from 0, not spinning, to 1, maximally spinning. Many observed black holes have spin parameters of 0.5 to 0.9, spinning rapidly but not maximally. The fastest spinning black hole found in the October 2024 merger approaches this maximum. As black holes accrete material, they can spin up if the material orbits in the same direction as the existing spin, or spin down if material orbits opposite. Black holes' gravity bends light so strongly that they act as gravitational lenses, magnifying and distorting background objects. Astronomers use this effect to find black holes and study them. When a compact object passes in front of a background star, the gravity magnifies the star's light temporarily, a microlensing event. By studying the magnification pattern, astronomers can determine the foreground object's mass. Several black hole candidates have been found this way, including isolated black holes without companion stars. These objects are otherwise invisible. They don't emit light and have no accretion disks. Gravitational lensing reveals them by how they warp spacetime. Black holes have shaped the universe's evolution in fundamental ways. In the early universe, the first supermassive black holes formed and powered bright quasars, ionizing hydrogen and helping end the cosmic dark ages. Active black holes at galaxy centers regulate star formation through feedback, preventing galaxies from converting all their gas into stars too quickly. Mergers of galaxies bring their central black holes together, eventually merging to form larger black holes and triggering bursts of star formation from the collision's shock waves. Gravitational waves from black hole mergers carry information about stellar evolution and galaxy formation history. Physicists sometimes find it useful to think of the event horizon as a membrane with physical properties, even though it's really just a boundary in space-time. The membrane paradigm treats the horizon as if it has temperature, electrical conductivity, and viscosity. Material falling through this membrane seemingly heats it, gets dissipated by its viscosity, and contributes to its conductivity if charged. These properties aren't real in the sense of being made of matter, but they mathematically describe how the horizon behaves from an external observer's perspective. The horizon's temperature is related to its surface gravity. By now, the answer to why can nothing escape a black hole is clear from physics. Space-time geometry curves so steeply that all forward paths lead inward, and the cosmic speed limit prevents anything from moving fast enough to escape. But the answer transcends physics, pointing to something deeper about reality. Black holes show us that the universe allows absolute boundaries, regions where certain questions, what's inside and can you return, have definitive answers, unknowable, and no. They demonstrate that nature doesn't always provide escape routes or second chances. They reveal time's arrow isn't just philosophical, but geometric. Inside the horizon, the future literally points toward the singularity. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Planets orbit stars. Stars orbit galactic centers. Galaxies orbit each other in clusters. All are circles, cycles, endless movements, like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast cosmos. You're part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like celestial bodies silently rotating in their paths. Unhurried, unresisting, simply existing. We're almost there now. There's something beautiful about absolute boundaries. In a universe where most things flow and change, where borders are porous and paths reversible, black holes stand apart. They say, here, the rules change. Here, forward is the only direction. Here, time becomes inescapable. This isn't cruelty, but clarity. The event horizon teaches us that some thresholds, once crossed, mark permanent transformation. Imagine light traveling across the cosmos for billions of years, crossing vast stretches of darkness. It moves forever at 186,000 miles per second, never slowing, never stopping. Then it approaches a black hole. The light doesn't sense anything unusual. Photons don't feel or know, but space-time curves around it, bending its path. If the light passes close enough, the path curves inward, toward the event horizon. The light crosses the boundary, continuing at its unchanging speed, but now all forward directions lead deeper inside. No force slows the light, no barrier blocks it. The geometry itself has changed, so the light's endless forward motion carries it to the singularity. Every atom in your body was forged in stars. Hydrogen formed in the Big Bang. Heavier elements like carbon, oxygen, and nitrogen were created in stellar cores through fusion. Iron and heavier elements formed in supernova explosions. These materials scattered through space, eventually coalescing into new stars, planets, and life. You're made of recycled stardust, atoms that once burned in stellar furnaces. Some stars that created your atoms ultimately collapsed into black holes, locking other material forever behind horizons. Those black holes still exist, scattered through the galaxy, containing atoms that might have become part of other worlds. Gravitational waves are sometimes called the sound of space-time, though they're not sound waves. When LIGO detects a black hole merger, researchers convert the gravitational wave signal to audio frequencies humans can hear. The result is a characteristic chirp, a rising tone that sweeps upward in pitch and volume, reaching a peak at the merger, then ringing down. This chirp represents two black holes spiraling together faster and faster, orbiting hundreds of times per second just before merging. The October 2024 merger GW 241011 produced a chirp with slightly different characteristics due to one black hole's rapid spin. Just outside the event horizon lies the photon sphere, a region where light can orbit the black hole in unstable circular paths. A photon traveling tangentially at just the right distance will loop around the black hole repeatedly. But these orbits are unstable. The slightest perturbation sends the photon either falling inward or escaping to infinity. The photon sphere contributes to the black hole's shadow seen in images. It's part of the dark region where light is captured. These orbiting photons are the last light that might escape. From a distant observer's perspective, time appears to stop at the event horizon. Light from infalling objects redshifts to infinite wavelength, effectively vanishing. The objects appear frozen at the horizon's edge forever. This creates a strange situation. The black hole appears to accumulate a frozen atmosphere of material that approached but never quite crossed from an outside perspective. Yet, from the material's perspective, it crosses smoothly and continues inward. Both perspectives are valid within their reference frames. This duality reveals something profound. The event horizon is a boundary not just in space, but in time structure. Some theories suggest black hole interiors might contain entire universes. When matter collapses past the event horizon, extreme conditions might trigger inflation, rapid exponential expansion, creating a new universe inside, disconnected from our own. This black hole universe theory is speculative, but mathematically, the interiors of black holes resemble expanding spacetimes. If true, every black hole might contain a cosmos, and our universe might itself be the interior of a black hole in a larger external universe. Some black holes orbit normal stars in binary systems, creating a gravitational dance. The star and black hole orbit their common center of mass, sometimes taking hours, sometimes days to complete an orbit. The star remains intact if far enough away, but the black hole's gravity tugs at it, creating tides that might distort the star's shape. If close enough, the black hole strips material from the star, feeding gradually. These systems show us black holes' effects on surrounding matter without catastrophic destruction. When black holes collide, space-time itself shows strain. Gravitational waves are literal distortions, stretching and squeezing space as they pass. During the peak of a merger, the two black holes distort each other's horizons before combining. The final black hole forms in a distorted shape, then rings down, oscillates like a struck bell, before settling into a smooth sphere. These ring-down oscillations are gravitational waves with specific frequencies determined by the final black hole's mass and spin. By measuring ring-down, scientists can test whether the final object is really a black hole with a smooth horizon. Light from distant quasars, powered by supermassive black holes, has traveled for billions of years to reach us. We see these black holes as they were in the universe's youth, when galaxies were forming and the cosmos looked very different. The black holes feeding then are now quiet. Their bright quasar phase ended. We see their history written in ancient light, snapshots from different epochs showing how supermassive black holes grew and evolved. Each ancient quasar is a time capsule, showing us the universe's past. Sagittarius. A star, our galaxy's central black hole, is remarkably quiet. Despite containing 4 million solar masses, it barely glows. The accretion rate is extremely low, a tiny fraction of what it could consume. If Sagittarius A star fed actively like distant quasars, it would shine brilliantly, outshining all stars in the galaxy combined. Instead, it's nearly dormant, only occasionally flaring when gas clumps or dust clouds fall nearby. This quietness is fortunate. An active black hole at our galaxy's center would flood the inner galaxy with radiation. Quantum entanglement creates mysterious connections between particles. Measure one, and you instantly know about its partner, regardless of distance. Some physicists propose deep connections between entanglement and space-time geometry. The ER equals EPR conjecture suggests that entangled particles might be connected by tiny wormholes, Einstein-Rosen bridges. If true, quantum entanglement and space-time geometry might be two aspects of the same underlying reality. Black holes, with their extreme space-time curvature and role in the information paradox, sit at the center of these ideas. If Hawking radiation is real, every black hole eventually evaporates completely, given enough time. For a solar mass black hole, evaporation would take approximately 2 × 10⁻⁶ years, an unimaginably vast span, far exceeding the current age of the universe by a factor of trillions of trillions. Supermassive black holes take even longer. A billion solar mass black hole would take about 10⁻⁻100 years to evaporate. As a black hole evaporates, it shrinks, becoming hotter and radiating faster. In the final moments, it glows brilliantly, releasing its remaining mass energy in an intense burst before vanishing entirely. There's a finality to black holes that mirrors life itself. Events have consequences we cannot undo. Decisions made cannot be unmade. Time flows forward only. We cannot return to yesterday, cannot unspeak words, cannot reverse aging. Black holes are physical manifestations of this irreversibility. Once crossed, the event horizon marks a transition that cannot be reversed, a threshold permanently behind you. This isn't metaphorical, but literal. The geometry of space-time inside the horizon points only one direction in time: forward, inward. General relativity's equations describe black holes with mathematical precision. The Schwarzschild solution shows how non-spinning black holes curve spacetime. The Kerr solution adds rotation. These aren't approximations, but exact solutions, describing geometry with perfect clarity. The mathematics shows inevitably, once you're inside the event horizon, all time-like paths lead to the singularity. There's no mathematical solution representing escape. This isn't a failure of technology or imagination. The geometry itself permits no return. Einstein's equations don't just predict black holes. They prove escape is impossible with the rigor of mathematics. Black holes mirror the mysteries of existence. We cannot observe the interior, just as we cannot directly observe another person's consciousness. We cannot reverse time inside them, just as we cannot reverse time in life. They contain information forever hidden, just as the past becomes increasingly inaccessible with time. They transform everything that enters into something fundamentally different, just as experiences transform us irreversibly. They connect the very large with the very small. They pose questions we cannot fully answer yet. Perhaps black holes teach us to appreciate limits. Not everything is accessible. Not every question can be answered through direct observation. Not every place can be visited and returned from. These limits aren't flaws in the universe, but features. They create structure, boundaries, definition. Without event horizons, black holes couldn't exist as distinct objects. Without causality's protection, physics might be chaotic and unpredictable. Limits create meaning. The horizon defines what a black hole is. Quantum mechanics tells us observation affects reality at small scales. Black holes raise the question: what does it mean to observe something behind an event horizon? Information from inside cannot reach outside. So in a sense, the interior is permanently unobserved from our universe's perspective. Some interpretations of quantum mechanics suggest unobserved quantum states remain in superposition, existing in multiple possibilities simultaneously, until measured. Does the interior of a black hole, forever unobserved from outside, exist in quantum superposition? Astronomers estimate the universe contains roughly 100 million stellar mass black holes in our galaxy alone, and similar numbers in each of hundreds of billions of other galaxies. Add supermassive black holes at most galactic centers, and the total might be trillions of black holes throughout the observable universe. Most are invisible, inactive, drifting through space. Together, they contain perhaps 1 billion solar masses of matter, significant, but still a small fraction of the universe's total mass energy. Standing at the edge of a black hole's event horizon, if you could somehow hover there, you'd face the ultimate unknown. Just ahead lies a region you could enter easily, falling forward, but from which you'd never return. The horizon itself looks unremarkable. Just empty space flowing inward faster than light. Stars shine above. The universe extends around you. But ahead lies profound mystery. What's the experience of crossing? What happens at the singularity? Is information preserved? Questions pile up, each leading to deeper mysteries. We, conscious observers made of stardust, contemplate black holes, objects that cannot contemplate anything. We're the universe studying itself, matter and energy arranged to create minds capable of understanding other arrangements of matter and energy. Black holes represent one extreme of this spectrum. Matter arranged with maximum gravity, zero consciousness, pure geometric form. We're the opposite. Matter arranged with minimal gravity, maximum consciousness, able to reflect and understand. Yet we're connected. The same physics governs both. Despite black holes' strange and absolute nature, we understand them. Einstein's century-old equations predicted them. Observations confirm predictions. We've photographed their shadows, heard their mergers, tracked stars orbiting them. We know their masses, spins, sizes. We understand why escape is impossible and can explain it clearly. This understanding doesn't dispel the mystery entirely. Profound questions remain, but it shows that the universe, despite containing extremes like black holes, follows comprehensible rules. Some things about black holes we may never know with certainty. We cannot observe the interior directly. We cannot verify exactly what happens at the singularity. We cannot watch Hawking radiation from real black holes. It's too faint. We cannot test quantum gravity theories in black hole interiors. These limitations are permanent, built into the nature of event horizons and causality. This requires acceptance. Some questions remain unanswered, not because we lack cleverness or technology, but because nature prevents certain information from reaching us. We've wandered through the physics of black holes, from event horizons to singularities, from gravitational waves to Hawking radiation, from observations across the electromagnetic spectrum to theoretical puzzles about information and quantum gravity. We've seen why nothing can escape. Space-time geometry combined with the cosmic speed limit creates an absolute boundary. We've learned black holes aren't just theoretical, but real, observed, understood objects scattered throughout the cosmos. We've explored how they form, grow, spin, merge, and perhaps eventually evaporate. Perhaps the most important insight is this: matter crossing an event horizon isn't destroyed or trapped in any ordinary sense. It's transformed. Outside the horizon, matter exists in the universe we see, participates in galaxies and stars and planets. Inside, it exists in a different way, in a region of space-time causally disconnected from the external universe, following paths we cannot observe. But it still exists, still has properties, still curves space-time. If information is preserved through Hawking radiation or encoded on the horizon, then nothing is truly lost, only transformed into different forms. And so, our quiet journey through black holes and their inescapable gravity comes to a gentle close. We've traveled from the mathematics of event horizons to the detection of gravitational waves, from spinning black holes in distant mergers to the quiet giants sleeping at our galaxy's heart, discovering along the way that space-time itself can fold into absolute boundaries, from invisible singularities to visible shadows, from the quantum uncertainty near horizons to the perfect predictions of Einstein's equations. We've glimpsed how black holes are both endings and gateways, not to other places, but to deeper understanding of space, time, and transformation itself. Black holes remind us that the universe contains both freedom and inevitability, both openness and absolute limits. They teach us that some transformations cannot be reversed, some boundaries cannot be crossed twice. Yet in studying these ultimate limits, we, the universe, aware of itself, demonstrate that understanding has no horizon, that curiosity reaches everywhere, that meaning emerges even from the darkest mysteries. And now, in these final minutes, take the deepest breath you can. Think about unity of every atom, every event, every moment in the cosmos. You are not separate. You are a link in an endless chain. Think about the unity of all matter in the universe. How atoms from ancient stars became the earth, the air, you. Some atoms fell into black holes long ago, hidden behind horizons. Other atoms, the ones that became you, continued their journey. You're made of possibilities that chose one path among infinite paths through space-time. Let your entire being dissolve into the gentle darkness, into the soft gravity of sleep pulling you downward, accepting, welcoming. Prepare for deep rest. No boundaries left, only peace. If this gentle journey through cosmic boundaries brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of black holes and event horizons to fade now, like stars disappearing as dawn approaches, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gentle gravity is pulling you down into your bed, into rest, into the comfort of complete stillness. If sleep comes, let it carry you like a particle crossing an invisible boundary, smoothly, inevitably, into a realm where time and worry no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the black holes will still be there, spinning through the cosmos. The event horizons will still mark their boundaries. Gravitational waves will still ripple through space-time. But tonight belongs to stillness. Tonight belongs to you, resting, dreaming, transforming in your own gentle way. Rest well, peaceful traveler, and remember, even light itself, traveling at the universe's maximum speed through the vast cosmic dark, sometimes finds a place to rest. Sleep well with gentle science. Good night.